think we step to the next presenter, which is Patrick Vonwirth from my group, and he will give a presentation about continuous inverse kinematics in singular positions. So Patrick, please start.
Okay, hi everyone. Can everyone hear me?
Yes, it's good.
So, okay, do you see my screen shared?
Yes.
Okay, nice. Then I will start. So I'm Patrick Vonwirth from the Technical University of Kaiserslautern, and I'm talking a little bit about inverse kinematics, especially in singular position of a robot, which unfortunately, if we go to some humanoid robot, should be the default case on straight-legged walking. So here is a small description of the problem of this singular position at the example of a very simple two-legged robotic arm, a two-segment robotic arm. If you can see here, the two velocity vectors of the joint S and E are in parallel as shown by the arrows. And now the problem is that we have this green area, which is a reachable workspace, and this red area, which is an unreachable workspace of this robot. Unfortunately, both in the same directions, perpendicular to the two velocity directions of the joints. So the problem here is that there is no velocity direction going into the green, but if there would be one going into the green, there would also be, as linearized, negative one going into the red, which is also not desired. So there are somehow two problems in once, and these are formulating a very nonlinear problem at this edge of the workspace of such a robot. So there are lots of existing approaches to solve inverse kinematics. Obviously, this is a very well-known problem, but unfortunately, over the years, lots of researchers and also mechanical engineers decided to overcome this problem by simply building their robots in a way that they do not go into this critical position. So every robotic arm has a very big angle normally in its arm to simply overcome this problem. However, if we want to go forward to some straight-legged walking, this obviously is not a very good solution, although it is absolutely fine for some robotic arm and industrial robots. So here I have listed some inverse kinematic approaches which are existing and which are not using any Jacobian. So there are, for example, this cyclic coordinate descent approach, which is especially designed to overcome very large distance problems. There are Monte Carlo simulations developed, some AI methods, and also some forward-backward reaching inverse kinematics algorithm, which is invented especially also for CGI applications to visualize artificial motions of creatures in films. But unfortunately, all these are, again, not dealing with this singular position. And also here this very classical approach, the Newton-Raphson approximation, is in general not able to really handle this position. However, this approach is very simple, it is very well known, and it is the base of my research. So I would like to very quickly introduce it. It is very easy, so it's more or less 3 steps. You make an error estimation, then you linearize in this error position, and then you make some damped update, and then you repeat until you finally reach your goal. And this linearization can be a lot of different things. So Jacobian inverse, transpose, pseudo inverse, whatever, everything will work in situations more or less well. Now, if we reformulate this middle part with the error estimation and the linearization here on the upper left side, we can very quickly just rewrite this equation to the formula on the right side, and it can be seen that it is more or less a Taylor approximation. If you compare this G, which is representing the goal of the kinematic function, which is the nonlinear function f, plus this nabla operator, which is here representing the first derivative of f in the Taylor approximation. So very simple. I just stated to extend this Taylor approximation by another element using the second derivative. This now redefines the general adaptation rule of the Newton-Raphson approximation to the equation on the bottom. So again, our goal is the position of the kinematic function kappa of the joints, and then the first derivative is the Jacobian, and then here on the right side added the second derivative of the kinematic function is now the first derivative of the Jacobian matrix. And this can very easily be written as a matrix multiplication by putting this Jacobians as a vector over each other, multiplying with a vector of the gradients delta I, which are representing the adaptations of the joints. Unfortunately, there is this x square in this equation, which cannot be found out in such a linearization. So therefore here also our goal is extended to this delta E and the delta E dot as a kind of second goal position, which at the end should be 0, because if we are very close to the goal position, the second derivative should be more or less not contribute anymore to the overall process. But in order to get this into account, the Jacobian derivative can simply be extended by the original Jacobian again with either plus or minus, dependent on the robot kinematic structure, what is nice. And now it is very easy that whenever this delta dot is required, which represents a nonlinear motion of the robot at the end, then automatically by this extension also the original delta will be acquired by this function. So this delta dot now can simply be neglected afterwards, and only this delta can be moved on to the iteration to come more closer to the goal by this original approximation algorithm. So here is now the picture what exactly happens. As you remember, the velocity vectors of the two joints S and E are again in this right picture, and now the derivative of the Jacobian is also added as vectors, which are these vectors that are going at 45 degrees into the reachable workspace area. I don't know if you see my cursor. I hope you see it. I'm pointing at it. And this is now exactly what we want to have. There is this one arrow which is going into the reachable workspace by this additional delta dot, and by especially setting this delta dot to be positive, the arrow into the negative direction can be completely avoided, so that there is definitely no way to go into the unreachable red workspace by this approximation algorithm. As a simple evaluation, I have taken the kinematic structure of the planar two-legged bipedal robot CARL, which can be seen here in the picture, and the kinematic structure can be seen on the right. It's very simple, two-segment leg and a foot, which is not really required for this problem. And there is a trajectory of a very simple circle of the ankle, which is half in the green path and half in the red unreachable workspace area. And here there is the result. Here there is the result of the tracking of this circular motion. So on the left side, there is the now extended version. On the right side, the original Newton-Raphson algorithm without this J dot extension. And you can see at around 30%, there is on the joint angles step. Oh, sorry, there is a step in the joint angles because there the robot is going out of the singular position, which is not covered in this original approach, only if the error is big enough and there is some big enough angle in between. But in the new approach, in this extended approach, this trajectory is very smoothly starting. The robot is continuously going out of the singular position. Maybe just a little bit more. If you project this trajectory onto a vertical line, you can see here that this original approach is simply doing nothing, because this Newton-Raphson algorithm is not able to go straight out of the singular position, while on the left side, the extended approach has absolutely no problems to deal with this. So thank you for your attention, and I would like to hear some questions from your side.
Yeah, Patrick, thank you very much for the nice presentation. We have time for a short question. Who likes to start?
Oh, hello, Patrick. Can you hear me okay?
I can hear you, yeah.
Yeah, my name's Clive Lockton. I'm editor of the Industrial Robot Journal. Just wondering, very, very interesting presentation. I thought it was very, very clear in what you were doing. How does this actually compare with the way that that human beings and other animals get around this problem? Are they totally dissimilar, or do you think there are? How do people tackle this problem as opposed to doing it numerically?
Well, this is okay. This is a very interesting question, but unfortunately, I cannot really answer this because till now, no one really knows how nature is dealing with this problem. But the fact is that we are dealing with this problem very well.
Yeah.
And industry robots are definitely doing not. So maybe we are doing something like this. Maybe we have learned some pattern to move our joints. Maybe we just know how to move the joints, because if we are in joint space and not in workspace, there is no singular position anymore. But this unfortunately it's a very good question, but I think this it's better to ask biologist or some neuroscientist.
Yeah.
Okay, I think we have to go ahead. We run a little bit out of time. So thank you also for the question. Maybe you can later on discuss a little bit. Patrick can send you his email.